In this lecture, we would be discussing about the blast furnace productivity. So, blast furnace productivity is defined as the ratio of the amount of coke burned, that is coke throughput or coke burning rate per day, to the coke consumed for a unit of iron, that is coke consumption rate in tons per ton of hot metal. So, we can say P, the productivity, is equal to the amount of coke burned Q divided by K, that is coke consumed per unit of iron or coke consumption rate. So, where P is given in ton hot metal per day, Q equal to the coke burned in tons per day and coke consumed in tons per ton of hot metal is given by K. There are various ways this productivity can be defined. So, this is one of the way commonly used, but there are many other ways by which it can be defined. So, the other way of defining it in terms of heat input. So, productivity is a ratio of total heat input per day to heat required to produce 1 ton of hot metal. So, heat input per day to heat required to produce 1 ton of hot metal and another definition of productivity is is in terms of rate of production, ton of hot metal per day divided by working volume of the furnace in meter cube. So, when we say the working volume of the furnace, this we have defined before in the beginning of this course. As such, the working volume is from tier to stock line that we take in calculation of this productivity definition. Nowadays, because we use quite a bit gas and PCI, those of fuel and other thing. So, there is another way of defining the productivity which took care of this fuel such as coal and oil. So, since coke is increasingly being replaced by auxiliary fuel such as coal, oil, etc., even some natural gases. So, it is appropriate to define the productivity now as total tier gas produced per day divided by tier gas generated to produce 1 ton hot metal. So, it is a ratio of tier gas produced per day and the gas generated to produce 1 ton of hot metal. So, sometime it is related also to the earth volume, which as such does not give the correct physico-chemical representation of the productivity. So, there are many ways by which as you can see the productivity of the furnace has been defined, but mostly this is a good way of defining the productivity in terms of coke burning now, because the coke burning now is being replaced quite a bit with PCI of fuel, and like that, if that is the case, then this would be a good definition of the productivity. So, blast furnace is a gas solid counter current reactor, and its productivity depends on how much you blow into it. So, how much air actually you can blow into it. However, the furnace can be driven to maximum pressure drop, and after that the process deteriorate. So, there is a maximum pressure drop across the whole furnace, and above that, if you keep it, then the furnace will deteriorate and your productivity will decrease. The above two factors depends on many parameters. So, next slide shows how the productivity of the blast furnace can be increased considering the effect of various parameters. So, as you can know, there are two things: how much you can blow into the furnace and the maximum pressure drop which you can reach safely without affecting the productivity. So, these two parameters, how do they get affected by other parameter, we will see in this slide. So, this is about if you want to increase the productivity, then as we saw in the first definition, either you decrease this and increase Q. So, increase Q means the amount of coke burn per day, that if it is increases, productivity increases, or coke consumption rate, tons per ton of hot metal, it should be decreased, then you can get the higher productivity. So, that is why how we can decrease the coke rate. So, it is a burden preparation, screening, sizing, agglomeration. So, use of hydrogen wearer material, or so in this one, because hydrogen has high reduction potential. So, it is then beneficial, it will decrease the coke rate, improve gas solid contact. So, if surface area can be increased and keeping the proper size of the material, free flux agglomerate. So, you agglomerate and use the fluxing agent. So, in that way also you can decrease the coke rate. For pre-flexing you use the agglomeration, sintering and other thing. So, also if you increase the blast temperature, that will also lead to decrease in coke rate. Most of these factors we have discussed before. Now, we are talking in terms of how they will affect the productivity. Fuel injection, of course, that also again you are substituting, so that will the fuel, so it will reduce the coke rate. Increase in direct reduction, we had discussed this one in details about the contribution of direct reduction and indirect reduction in the production of iron, and what would be the optimum value of both of that. So, one can do that one, and that is going to decrease the coke rate if one can achieve that optimum indirect reduction reaction. And so, that this leads to decreased thermal load. So, this all is going to decrease your coke rate, your productivity is going to increase. On the other end, it is about the Q factor, which coke throughput, which we said. So, that if we can increase Q, naturally our productivity increase. And how the Q is affected by other parameter? One, sizing, beneficiation, mechanical strength, lower slag. Of course, sizing is very important, and beneficiation is also important. If you take care at this stage, you can reduce slag volume. So, you do not have to put that much your silica or lime. So, the slag volume also will decrease, and not only that, if you decrease the slag volume, means the chances of flooding would be low, and you can blow more volume in the blast furnace, and that is one of the things which we had mentioned previously. So, that will help in blowing more blast furnace without getting it flooded. So, it is very important. Increase mechanical strength, this is by using agglomerate, and as we had discussed before, how you can control the quality of these agglomerate and try to get, reduce the thickness of the cohesive zone, and should move to high temperature zone, and that will again help to increase the coke throughput. Lower slag volume we already discussed. So, this is in the burden preparation, and if we can increase the coke strength, this is also very important, because coke is taking part in many things in the reaction, and when the gaseous reaction is occurring, that time actually coke is getting gasified. So, strength becomes down, goes down, it becomes more porous, and near the dripping zone and the tear, it has to go with lots of attrition and harsh condition. So, coke quality is very important. If we can maintain that, we can have increased coke throughput. Similarly, permeability of the region, this is I do not have to emphasize, we have devoted lots of time on this previously, which directly affect the productivity. If permeability is not good, then you will be having a high pressure drop, high resistance to the gas, and you can't blow much volume into the blast furnace, and that is ultimately is going to decrease your productivity. High top pressure is also one of the things we will discuss little bit again in this, and that high top pressure actually lead to increase in volume, blow volume in the blast furnace. So, that certainly is going to increase the coke throughput and increase the productivity. You can of course humidified and oxygenated the blast furnace, which we talked, that will increase the flame temperature and other thing, and probably will increase your coke throughput. So, and even the fuel injection. So, this is the way we can increase Q factor, which ultimately increase the productivity of the blast furnace. So, these are the factors which affect the blast furnace productivity. Many of them we have discussed before, but I will touch upon some of the important one here again. So, most of the parameter we have discussed in previous lecture, so not repeated again. The effect of some parameters are shown in this table. So, effect of percentage contents of plus 10 millimeter fraction of ore in the blast furnace. So, base condition is this. So, plus 10 millimeter not that 54%, if you increase that one to 71%. So, savings you can see how much 58, these are actual plant data. So, coke saving 58 kg per ton of hot metal. If you increase to 88 or increase to 89, you can save almost 90 kg per ton of hot metal in this one. So, very important of having a good size in the blast furnace, or more in a way the uniform instead of mixed. Fuel dust, flue dust also, because you have already saved the coke and other thing, and because you are having a more 10 millimeter size, certainly flue dust is going to decrease. So, it decrease for 90% of millimeter size ore from 254 to 137, almost half, 45% or so, and that is a big reduction, and that is a good saving, especially in the gas cleaning system, electrostatic precipitator and other things. Performance increase from 100 to 110% of blast furnace. Volume utilization, meter cube per ton of hot metal is almost 0.83 from 0.91 in 24 hours, and coke burning rate also decrease per ton per meter cube from 1.1 to 1.2. So, one can see the benefits of having a closed size range, this burden, and plus 10 millimeter in the size range, having more percentage in it. So, ore size also now we said only one plus 10 millimeter. Now, see the effect of different ore size. So, ore size in 2 or 3 categories indicate that all layers of one size are fed after a few hours of ore size 2 layers and so on. So, you do not mix the wider range size ore into one, but you separate them into 2 or 3 categories to narrow down the size range. So, that voided does not deteriorate. This is actually quite important. In practice, actually it is very difficult to maintain one size due to various reasons. However, one thing can be done anyway, screening is done, you can divide that charge into 2-3 categories, and if you do that way, as we had seen before in the lecture, the mix charging layer and in the stock, when they are mixing, the permeability is reducing, the void is reducing. Same thing is happening here, because if you have a higher size of particle and then putting immediately the lower size one, then they will settle in the interstices of the bigger particle, and then will reduce the permeability of the charge, and that will create a problem. So, this shows the effect of that. So, if you are having a mixed or everything mixed together, percentage of CO2 in the top case is 11%, which means you are probably having a more CO. So, it is not properly utilized. Coke rate is very high, but of course, these are the old data. So, coke rate is very high, almost 1.2 ton per ton of hot metal. Of course, no increase in the output. Now, if we divide this one into 2 categories, 2 size categories, you can see the CO2 in top case has increased, indicating good utilization of CO, and even the coke rate has decreased almost by 100 kg, and the output has increased almost by 9%. And if we divide further down into 3 categories, so more close range we are doing it, though we are having a same material, same charge, only thing what we are doing, we are dividing it into 3 categories, 3 different sizes, and narrowing the size range. If we do that way in 3 categories, it is substantial increase in CO2 in the top gas, which means much more utilization of the reduction potential of the gas, and the coke rate has decreased again quite substantially, almost from here to 220 kg, and this has gone to 18%, more than that output has increased. So, one can clearly see how the production or how the ore size is affecting the product or output. So, these are few practical things which in the blast furnace can be done to increase its productivity. This figure again is emphasizing more about the size range of the charge, or here in ore size. So, iron output, you can see when ore size between 9 to 50 millimeter, though it is also a wide range, but still one can see, and the percentage of coke size is this, your productivity with the coke size actually is increasing quite substantially. Now, if you increase this range, instead of decreasing, you are increasing. So, more what will happen, the smaller particle will occupy the space in between the big particle and will reduce the permeability of the charge, and that is where you can see the production is decreasing, though with coke size percentage increase, but quite substantially it has decreased. And if this range is too high, say 9 to 150 millimeter, then it is a very bad situation. Then certainly the permeability will deteriorate quite a lot in that case, and certainly your ion output will decrease, decreasing substantially with increasing of the coke size in this range. So, that shows again the importance of controlling the charge size or adopting the procedure categorizing the charge size into 2 or 3 categories and then feeding it into the blast furnace, and that will certainly increase the productivity of the blast furnace. And when we talked about the size and other thing, you can also see another thing from this. As your size decreases, you can see more heat transfer and mass transfer takes place, especially below 10 millimeter. It is sort of increase bit exponential way. So, because the surface area is very high, when the size is less than 10 millimeter, the surface area is very high. So, heat and mass transfer certainly would be very high. However, the flow resistance to fluid flow will increase substantially, because the surface area is very high, that will also give a big resistance to the gas flow, and this is not desirable at all. And if it is a big resistance, you can't put a more volume into the blast furnace, your productivity is going to decrease certainly. So, one has to optimize that thing. So, this is not a very good situation at all. So, its particle size below 10 must be avoided and should not be fed into the blast furnace. And if you look at the plus 20 mm particle size, there is not much difference in the heat and mass. Of course, a little decrease, but it is not substantial. So, one can avoid minus 10 millimeter and can go towards a little larger size particle, and if you look at that way, the productivity reach to the maximum about somewhere when your particle size is about 45 millimeter or 4.5 centimeter. And so, that is where the highest productivity you have. You can blow more air, less coke rate, and good heat and mass transfer. Flow resistance is also less in that case. So, this shows how the effect of size or size affect the mass transfer, heat transfer, and fluid flow. Now, we will talk another parameter, that is flame temperature, which also affect the productivity of the blast furnace. So, very high flame temperature may be disadvantageous, because production of large amount of SiO, which so as you have a high flame temperature, we had discussed that at high temperature SiO is formed when we were talking about the silicon transfer reaction. So, production of large amount of SiO, which lowers the voidage in the upper part by reoxidizing into SiO2 and depositing there. And we did mention about it that SiO is not that much useful. One, of course, it is absorbed in the liquid metal, it increase the silicon content in the iron, And another one, it also travels upward, which is the cooler region 1300 like this, and even less cooler, then it reoxidizes from SiO2, which is solid, it deposits in between the void edge, reducing the permeability, affecting the productivity adversely. Excessive volatilization of alkalis contributing toward the breakdown of burden and coke. This also we discussed in the starting, the bad effect of alkali and the alkali cycle. At the lower part of the blast furnace, temperature is high, so they vaporize, go up, and they condense, deposit there, and again come down with slag, and this cycle keeps on, and this also contribute alkali deposits into the charge in the breakdown of the burden. So, fines will generate. So, this is also not a very good thing. So, excessive temperature can further deteriorate this situation. So, this next figure shows about this thing, how these different things are there reacting in the blast furnace. So, this is a TUL level. If you look at the coke size, so you will see that at the TUL level the coke size is about 25 or 30 millimeter. So, you are feeding about 50 millimeter size in the starting, and by the time it comes to the TUL region, it reduces almost 50%, and even if it reduces 50%, one has to make sure this coke, because this is the harshest condition in the blast furnace here, is moving in the raceway, attrition, all those things are happening. It should be able to withstand all these things, even though it has reduced to 50% in size. So, this shows most of the reduction of this coke is occurring from, would say, valley region to TUL region rapidly, and nothing little bit here, but nothing much in the thermal reserve zone. Same thing, you can see the coke drum strength is quite good until stock line, but once it comes to cohesive zone in both region, it decreases, but still it has maintained near the TUL level almost 86. So, not that much decrease, that is a good indication. So, coke it's almost 86% of its strength, and reactivity of the coke increases from almost like 25% to almost 40%, somewhere in between reaches maximum, and that we could think that it is maintaining its reactivity, which is important to produce CO. And if we look at the alkali production, that is very low in, at the top, but it is comes down, alkali percentage increases, it becomes quite high in the middle zone, almost in the belly region or cohesive, and at the TUL then it start decreasing. The region of maximum here, because most of the vaporization of this alkali is occurring here, which builds up, goes up and condense and builds up there. So, there you have a maximum alkali content, and it comes with the slag and again recirculating and deteriorating the quality of the burden. So, one has to be careful about the percentage of alkali in the ash. So, this is a typical distribution of these coke size, coke strength, reactivity, and alkali in the blast furnace from top to bottom. And due to this alkali input, as we said, that because the permeability increase, as you can see, as the alkali input increases in kg per ton of hot metal, it will adversely affect the permeability of the burden, and similar then the production will go down. So, productivity also decreases, which is quite clear from that. So, alkali percentage should be kept minimum as much as possible in the raw material. So, like a beneficiation, other thing can take care of it.